start out with an example of what we mean by this phi function. This is called the Euler phi function. Some people say that it measures the primeness of a number, how prime a number is. Now, phi of any prime number is just 2, because there's only 2 divisors of, phi of any prime number is the prime number minus 1, because every number less than the prime number is relatively prime. Let's look at this example right here, okay? The answer to this is 6, and I'll write down the values here. You can list 1, 2, not 3, because 3 and 9 are not relatively prime, since 9 is 3 squared. So we have 4, 5. We have to skip 6, right? Because 6 is 2 times 3. And then we have 7 and 8. So notice the count right here is 6. You see, I wrote down 6 here. There's 1, 2, 3, 4, 5, 6 numbers that are relatively prime to 9. And so phi of 9 is said to be 6. Now, another thing that's quite interesting that comes in very handy here, and I'm going to actually prove it in another video, is that this is equal to 3 minus 1. And I'm going to write it this way for emphasis here. 3 minus 1 times 3 to the 2 minus 1. Okay? And the reason why I'm doing it like this is to emphasize that 9 is equal to 3 squared, right? And so this little result here is true for all primes. It's not hard to prove or see, actually, okay? Notice this does equal to 6 right here, right? This would just be 3 times 2, which is 6. Okay, so let's keep that in mind as we move along. Now, we're trying to show that phi of n squared is the same thing as taking n and multiplying it by phi of n. We're trying to show it for all natural numbers. So a very common starting problem for any number theory proof is to write the prime factorization of the integer. And so these p's are distinct here. So let me write that in. Your p sub i's are distinct. And the k's are just natural numbers, greater than or equal to 1. Okay, so I'll just write distinct, all right, there, abbreviated. Now, since we're interested in what happens to n squared, we square each of the exponents. That's just laws of exponents. You multiply the exponents. You actually elevate it to that power, and then you can multiply the exponents, and so this is the final result. Okay, let's keep going. Now, another result that I'm going to use that I won't attempt to prove, but it is important number theoretically. This is said to be multiplicative, so that means you can split it up as long as the arguments are relatively prime. So it's a multiplicative function. Let me see if I can spell that. Multiplicative. All right, and a multiplicative function is one that you can split as long as the input values are coprime or relatively prime. And of course, these prime powers are relatively prime to each other since they are posited to be distinct right here. Okay, let's keep on going. So we're going to use the multiplicative. This part right here is because phi is multiplicative. And then this result is what I just wrote down. And this is a fun result, and I'm going to prove it in another video. But it essentially, you can, there's p raised to the r minus 1 multiples of p that won't be relatively prime to p to the r. And so you have to subtract them off. That's more or less in a nutshell of how the proof would go. A little more detailed than that. Okay. But what we're going to do is repeatedly use this result. And notice this is the result that I wrote down right here. Okay, p minus 1, 3 is the prime number, and then 3 to the 2 minus 1. Okay, so you're subtracting the x from the exponent here and from the prime number itself here. It's not too hard to remember. So this result right here is actually what this says in the general case down here. Okay, so the rest of it is about crunching exponents, folks. Notice this is just nothing more than brute force using this over and over and over. Okay, we just, to write this statement down, we use this result over and over and over m times, okay? Now, what we do is do some rearranging here. We got, notice that we have each prime raised to the 2 to the k minus 1. Okay, well, you see how we take k of them away, right? So you see this k1 would have been part of 2k1 here, and then the minus 1. You see how we're splitting stuff, folks? All the k's, we're just taking away k from the 2k sub I minus 1, laws of exponents. In other words, if you juxtapose this green object right here with this object right here, you get this term, and so on, okay? All right, and so you can recognize this, of course. The green part is just n, okay? The green part right here is just n, okay? And the rest of this, folks, is just going to be phi at n by repeated utilization of this result right here. Okay, how do you make the phi? I always forget that. Okay, I'm going to make it like that this time. Okay, so this would be phi of n times n right here. So you see this part is in this, I'm sorry, this part is just phi of n. Let me erase that. Okay. Okay, so y'all, this part is in. Okay, and then let me get the marker working again. Okay, and this part right here is phi of n, which is what we were trying to prove. We were trying to show that phi of n squared, which is what we started with right here, is equal to n times phi of n. Okay, and we did that. Okay, so we can write QED here. Well, I got a smaller marker. Okay, smaller. All right, so now let's just look at a concrete example of that. Let's do maybe. Am I still going to be able to write down here? Let's see. Okay, yeah. Let's try. Phi at 7 squared. Okay. Okay. The result we just established here said that this will be 7. This will be 7 times phi at 7. Like that, folks. And so this would be equal to 14, 7 times, or excuse me, phi of any prime number is, you decrement the prime number one time because everything less than the prime would be relatively prime to the prime number. So this would be equal to 7 times 6 equals to 42. All right. So perhaps it diminishes the computation of doing phi at 7 squared, although there's a result for that too. You know, I think you could also call this 7 squared times 1 minus 1/7. That follows more or less from this proof right here. It's just rewriting this in a different way, I guess. But this is pretty well known right here. You don't have to worry about squaring the prime or anything. So this would be 49, times 6 over 7? Okay. And again, this result actually is this result just written by dividing by p, I guess, or doing something like that. Okay. So, multiplying by p and dividing by p at the same time, maybe. All right, but that is also equal to 42. Okay. So again, it's a lot of symbol mashing, folks. These two results are the same right here. But anyway, all I wanted to do was just prove this result right here, which we just did. And I think this is true in general, like this would be phi at n cubed. I think you would have n squared here times n, I believe. I'm not sure, I think so, or maybe the other way around. But in any event, we did prove this number theoretic result. And the linchpin was the fact that phi is multiplicative. And this result right here, which does require some proof, all right? Okay, that is all.